The story begins in October 2017, when astronomers spotted something zooming through our solar system that definitely did not get an invitation. It was moving too fast to be from around here, shaped like no asteroid we had ever seen, and left everyone staring at their telescopes thinking, "Wait, what was that?" Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes, it's best enjoyed the way you'd enjoy a late-night conversation. Quietly, with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure. Only if you enjoy these calm journeys through the universe. Now, let's begin. The moment was ordinary at first. Astronomers at the Pan-STARRS Observatory in Hawaii were scanning the heavens as usual, their powerful telescopes sweeping the night sky for anything that moved. The universe is full of wanderers, asteroids, comets, bits of space dust. But every now and then something shows up that doesn't play by the rules. This particular streak of light moved in a way that made no sense. It wasn't orbiting the sun like our local objects do. It was barreling through the solar system as if it had somewhere better to be. It was as if the cosmos had tossed a message in a bottle, and that bottle had just crash-landed on our doorstep, stayed for a few moments, and then zipped away before we could even open it. The first data showed it came from above the plane of the solar system, diving in steeply toward the sun, then slingshotting back out at an angle so sharp it could never return. Its trajectory was unmistakable. This was a visitor from another star system. For humanity, this was a cosmic first. Everything we had ever studied, every asteroid, every comet, every space rock, belonged to our solar neighborhood. We had theories about interstellar objects before, but theories are like those friends who promise to visit and never do. Oumuamua was the one that actually showed up, unannounced, holding a cosmic suitcase and a look that said, "I won't be staying long." Imagine the scene among astronomers. The discovery triggered a flurry of excitement that spread faster than gossip at a physics conference. Observatories around the world scrambled to point their instruments at the mysterious speck of light before it disappeared into the void. The problem? It was already leaving. Every hour mattered. The object was fading, shrinking, vanishing from view, like a flashlight moving away down an endless hallway. At first, scientists thought it was just another comet. That would have been the safe, sensible explanation. But comets usually have the decency to announce themselves with bright tails of vaporized ice, like celestial party streamers. This one had none. No plume of gas, no fuzzy halo, just a clean, sharp streak. The kind of minimalism that says, "I'm not here to impress you." The more they measured, the stranger it got. Its speed was incredible, around 87 kilometers per second relative to the sun. To put that in human terms, if you fired it from Earth, it would pass the moon in less than 5 hours. It wasn't just fast, it was fast enough to escape our sun's gravity entirely. This thing hadn't just wandered into the solar system. It had entered and was leaving in one smooth, uninterested motion, like a tourist who realizes they booked the wrong destination. Astronomers could trace its path backward and see that it came from the general direction of the constellation Lyra. Not from a specific star, but that region of the sky. It had probably been traveling for millions, maybe billions of years. Think about that. This object had been drifting between stars for longer than humans have existed, possibly since before our solar system even formed. It had crossed the dark, empty stretches of interstellar space, places so lonely that even light takes years to reach the next thing. Then, purely by chance, it passed close enough to the sun for us to notice. That cosmic luck is staggering. Space is so vast that it's like trying to spot a single grain of sand thrown across an ocean. Yet there it was, visible for a fleeting few weeks. Scientists rushed to name it. The chosen name, Oumuamua, comes from Hawaiian, meaning scout or messenger from afar arriving first. A perfect fit. The name carried a sense of mystery, of something ancient and intentional. It gave personality to what was, by all scientific measures, just a rock. But somehow, it felt alive in the imagination. The truth is, Oumuamua didn't just stir data charts, it stirred emotions. Humans have always looked up at the stars and wondered what's out there. We've sent our own probes into deep space, Voyager, Pioneer, New Horizons, but this was the first time something came to us from another world. It made the universe feel both smaller and infinitely more mysterious. In the days following the discovery, theories began to swirl faster than the object itself. Some astronomers compared it to an asteroid that had been ejected from its home system. Others whispered that its strange motion could mean something far weirder. But at this early stage, the facts were simple and astonishing. This was an interstellar traveler, the first we had ever seen moving through our cosmic backyard. For centuries, science fiction had dreamed of messages from other stars, alien artifacts drifting between suns, and mysterious objects that awaken our sense of wonder. And now, reality had delivered something almost poetic, a real-life mystery that could fit right into a sci-fi movie trailer. If the universe had a flair for drama, this was it. In that moment, Oumuamua reminded us of one essential truth about science. Discovery often starts not with answers, but with confusion. Something unexpected appears, breaks the rules, and suddenly everyone's scrambling to rewrite what they thought they knew. It was humbling, thrilling, and more than a little weird. The solar system had received a visitor from the stars, and it didn't even slow down to say hello. The Pan-STARRS telescope in Hawaii was the first to notice it. A faint streak of light darting across the sky at an impossible speed. At first, scientists thought it was a regular comet, but it had no tail. Kind of like a cat with all the attitude but none of the fur. To understand just how remarkable that discovery was, you have to picture what a night at Pan-STARRS looks like. The observatory sits on the summit of Haleakala, a volcano on the island of Maui, where the air is so clear it feels like the universe left the windows open. Its name stands for Panoramic Survey Telescope and Rapid Response System, which sounds like a superhero organization that fights cosmic crime. And in a way, it does. Its mission is to scan the entire visible sky every night, hunting for anything new. Asteroids that might threaten Earth, comets just waking up from their icy slumber, and the occasional mysterious visitor that breaks every rule in the book. That October night in 2017 began like any other. The telescope gathered thousands of digital snapshots of the heavens, each pixel filled with starlight. Later, Computers compared those images to previous ones, looking for anything that moved. It's the celestial equivalent of those spot the difference puzzles, except the differences are light years apart and the stakes are slightly higher than winning a sticker. When Oumuamua first appeared, it was little more than a pixel, a moving speck that streaked across the image frames. Automated software flagged it as something worth checking out. Nothing unusual there. The system finds hundreds of moving objects each week. But when scientists calculated its orbit, the numbers refused to behave. Normally, solar system objects trace neat ellipses around the sun, like cosmic clockwork. This one didn't. The calculations showed a sharply hyperbolic path, an open curve that meant it wasn't bound by the sun's gravity. It was just passing through. Imagine the collective double-take that rippled through the astronomy world. People rechecked the data, ran simulations, and recalculated trajectories as if hoping the numbers would eventually apologize for being so weird. They didn't. This thing had come from beyond the solar system and was already on its way out. The initial classification labeled it as a comet because comets tend to come from the outer reaches of the solar system and move unpredictably. But within days, follow-up observations showed no sign of a coma. The cloud of gas and dust that typically surrounds a comet's icy core when it approaches the sun. The object stayed stubbornly clean. It was as if someone had erased the comet's signature flourish, leaving behind only the bare essentials: a body, a path, and a mystery. Astronomers began scrambling to get more telescope time. Oumuamua was dim and fading fast, visible only through some of the most powerful instruments on Earth. Every night lost meant less data, fewer chances to figure out what it was. Telescopes from Chile to the Canary Islands to Arizona turned their eyes toward the same patch of sky. Observatories coordinated like detectives pooling clues from a crime scene, each one trying to get a clearer picture of the interstellar suspect. Meanwhile, the world beyond astronomy started to catch on. News outlets ran headlines about a visitor from another star. Twitter lit up with excitement. Everyone from science enthusiasts to sci-fi fans wanted to know what it was. For the first time, people who had never heard of pan-stars were suddenly captivated by an image of a streak barely visible against a field of stars. It was as if humanity collectively leaned closer to the night sky and whispered, "You're telling me something from another solar system just passed by?" The timing made it even more poetic. We had just begun to discover thousands of exoplanets orbiting other stars, worlds beyond our own system. But those were distant, unreachable points of light. Now, suddenly, a piece of one of those alien systems, maybe a shard from a shattered planet, or an ejected fragment from a young star's birth, had wandered into our cosmic backyard. It was like getting a piece of mail from a stranger who lived across the galaxy. The initial observation reports moved fast through the Minor Planet Center, which tracks small bodies in the solar system. The data was quickly refined, and the object received its first temporary name, C-2017-U1. The C stood for comet, because no one quite knew what else to call it yet. Within days, when it became clear it lacked a tail, the classification was changed to A-2017-U1, A for asteroid. But even that didn't fit. It was like trying to categorize a platypus when you've only seen mammals and birds before. It broke all the categories. So the naming committee did something special. They gave it a proper name from the Hawaiian language, Oumuamua, pronounced O-mu-a-mu-u-a. It translates roughly to a scout or a messenger sent from afar arriving first. The repetition in the name adds emphasis, as if to say, a messenger from very, very far away. The symbolism wasn't lost on anyone. It wasn't just a rock. It was a cosmic messenger, carrying with it stories from another star system we might never visit. The discovery also marked a turning point in how we think about space. Before Oumuamua, the idea of interstellar debris visiting us was purely hypothetical. We assumed the odds were microscopic. Space is big, and objects between stars are rare and widely scattered. But here it was, a piece of evidence that interstellar traffic actually happens, and we just hadn't been looking carefully enough. And in that realization was a subtle thrill. If one interstellar object had come through, others surely had too. Maybe they'd slipped by unnoticed, too faint or too fast to catch. Oumuamua wasn't just a one-time curiosity, it was a wake-up call that the universe is more dynamic than we thought. Stars form, planets break apart, and sometimes debris gets flung into the dark until it drifts into another star system's front yard. The team at Pan-STARRS didn't just spot a distant traveler, they opened a new chapter in astronomy. In a single week, they turned an anonymous blip of light into a discovery that would redefine how we see our place in the cosmos. The moment Oumuamua was detected, humanity's address expanded. We weren't just residents of the solar system anymore. We were part of an interstellar neighborhood. And somewhere, maybe light years away, another civilization might have its own pan-stars, catching sight of one of our outbound probes and wondering, wait, what was that? Oumuamua, which means scout or messenger in Hawaiian, was clocked at over 87 kilometers per second relative to the Sun. That is fast enough to escape the solar system completely. Imagine Earth trying to text it, wait, where are you going? But it's already halfway to interstellar space. Speed in space is a strange thing. We tend to think of fast in car terms. Hundreds of kilometers per hour feels thrilling, and anything above that gets terrifying. But in the vacuum of space, speed isn't just about how fast you're going. It's about whether gravity can ever slow you down. Every planet, every moon, every star has an escape velocity, the speed you need to outrun its pull. For Earth, that's about 11 kilometers per second. For the Sun, the big boss of our solar system, it's around 600 kilometers per second if you're starting from its surface. So, when astronomers realized that Oumuamua was cruising along at 87 kilometers per second, about 200 times faster than a speeding bullet, they understood immediately that this thing wasn't bound to the Sun's gravity at all. It was a drifter, just passing through, using the Sun's gravity as a cosmic slingshot on its way back into deep space. To put it in perspective, if it were headed for Pluto, it would pass it in less than 2 days. That's not interplanetary travel. That's a galactic drive-by. But here's the kicker. Its speed wasn't random. Astronomers could trace it backward through space, and it became clear that Oumuamua had entered the solar system moving at about 26 kilometers per second relative to the average motion of nearby stars. That's roughly the speed you'd expect for something drifting lazily through the galaxy. Not the result of any particular engine or explosion, but simply the quiet momentum of an object that's been coasting between stars for perhaps hundreds of millions of years. What gave it that speed in the first place? That's the fascinating part. Interstellar space isn't just empty, it's littered with the debris of creation. When stars form, gravity pulls gas and dust together, and the leftover bits, asteroids, comets, planet fragments, get tossed around like cosmic shrapnel. Some pieces get ejected entirely, slung out of their home systems by the gravitational dance of giant planets. Once that happens, they drift endlessly through the galaxy, unclaimed by any star, moving fast enough to cross the space between suns. Oumuamua, most likely, was one of those homeless wanderers. Its speed, then, wasn't a mystery in itself, but its behavior at that speed was. When something moves that fast, even small deviations in its path can tell you a lot. As it approached the inner solar system, it accelerated slightly, as if the sun were giving it a little nudge. That made sense. Gravity does that. But as it left, it didn't decelerate quite as expected. There was an extra push, a tiny but measurable acceleration, not fully explained by gravity alone. For a while, this puzzled scientists. Could sunlight itself be pushing it? After all, light carries momentum. Over long enough distances, photons can act like a gentle breeze, nudging small objects in space. It's the same principle behind solar sails, thin, reflective structures designed to ride on sunlight. If Oumuamua was unusually light and reflective, maybe that's what gave it the extra speed. It would have been the first naturally occurring object ever seen to do that. But that explanation opened a whole new can of cosmic worms. For one, it required Oumuamua to be extraordinarily thin, perhaps less than a millimeter thick, like a giant metallic leaf. No known natural process produces rocks that thin and flat. It would have to be something like a fragment of a larger body, shaved down by some unimaginable cosmic event. Or, as a few bold thinkers suggested, maybe it wasn't natural at all. Maybe it was artificial, something built to travel between stars, propelled by light itself. That idea turned heads. Not because everyone suddenly believed in aliens, but because the data left just enough room for the imagination to creep in. A light sail, a thin sheet of material designed to catch starlight, would behave exactly as Oumuamua did. It would pick up speed as it left the sun, and it wouldn't need a tail of gas or debris to explain it. Of course, proposing that meant stepping into the most dangerous territory in science, the zone where your colleagues raise an eyebrow and ask if you've been watching too much Star Trek. Still, the speed didn't lie. It was the most defining feature of Oumuamua's visit. Not only did it mark it as an interstellar traveler, it also guaranteed we would never catch it again. Even if we launched a probe immediately upon discovery, using our fastest rocket available, it wouldn't have been able to catch up. Oumuamua was already too far, moving too fast, and heading toward the outer darkness with a smug kind of finality. It came. It confused, it conquered, and it left. That realization hit astronomers like a cosmic joke. They had just detected the first known visitor from another star system, and it was vanishing faster than they could study it. It was like finding a golden ticket to the universe's greatest mystery, and then watching the wind carry it away. Within a matter of weeks, it had grown too dim to observe even with the world's largest telescopes. By early 2018, it was effectively gone, a receding spark swallowed by the black. The velocity wasn't just a number. It was a clue to the nature of the galaxy itself. It told us that interstellar space isn't a quiet void but a dynamic highway, full of fragments drifting between stars, moving on ancient trajectories we barely understand. And somewhere out there, countless other objects are doing the same, each with their own origin story, their own launch event, their own impossible speeds. Oumuamua's velocity taught us humility. It reminded us that while our rockets still struggle to leave the solar system, nature casually tosses rocks between stars like a child skipping stones across a pond. And those stones don't wait around for us. They just keep moving, indifferent to our curiosity, cruising through eternity at a pace that leaves human technology in the dust. The truth is, the universe doesn't owe us answers. Sometimes it just flashes by, waving a fragment of mystery at 87 kilometers per second, and leaves us with the cosmic equivalent of a "you had to be there." Unlike anything else we had catalogued, Oumuamua was long and thin, estimated to be 10 times longer than it was wide. Some said cigar-shaped, others said pancake-shaped, proving that even in science, people can't agree on breakfast. When astronomers first pieced together the object's light data, they realized something was very off. Normally, when you observe an asteroid or comet, its brightness doesn't change much as it spins. A sphere looks pretty much the same from every angle. But Oumuamua wasn't playing by those rules. Its brightness fluctuated wildly, by a factor of 10, as it rotated. That meant it wasn't spherical at all. It was stretched out, dramatically so, like a cosmic baton twirling through the void. Now, you can't just zoom in on something billions of kilometers away. We never saw Oumuamua's shape directly. Instead, astronomers had to infer it from how sunlight bounced off it as it tumbled through space. Think of it like trying to guess the shape of a thrown object by watching how the light glints off it. One moment bright, the next dim, repeating again and again in a 7-hour rhythm. That pattern was the object spinning. But the extreme brightness changes meant one side was reflecting a lot of light while the other barely any. At first, models showed it might be cigar-shaped, about 400 meters long and only 40 meters wide. It would have been like a skyscraper laid on its side, spinning end over end. The mental image was irresistible. The first interstellar visitor, long and sleek, gliding silently through space. It was hard not to imagine it as an alien spacecraft cruising under stealth mode. Even the most grounded scientists could feel a flicker of science fiction wonder in that idea. But then, more careful modeling began to suggest something even stranger. The brightness variations could also fit a flat object, one shaped more like a pancake or a shard than a cigar. That was when the debate began. Was Oumuamua the universe's most interstellar breakfast item, or was it more like a splinter of rock peeled from a larger body and flung into the dark? Both possibilities were bizarre. In our solar system, we simply don't see objects like that. Most asteroids and comets are roughly lumpy or potato-shaped. Irregular, yes, but not extreme. The idea of something so elongated, or so thin, was nearly unheard of. Whatever forces had shaped it must have been extraordinary. If it really was long and cylindrical, that could point to violent origins. Imagine a planet colliding with another body, the resulting debris flung outward, and one particularly tough fragment stretched by tidal forces as it escaped. Over time, smaller impacts or erosion by cosmic radiation could have smoothed it out. It might be the interstellar equivalent of a splinter chipped off in a galactic accident millions of years ago. On the other hand, if it was flat, that told a different story. Some researchers speculated that Oumuamua could have been made of layered material, maybe ice and dust, that evaporated unevenly as it passed close to its home star. That heating could have stripped away layers, compressing it into a wafer-like shape before launching it outward. Essentially, a cosmic flake pastry baked by stellar radiation. Either way, the shape made it unique. It wasn't just strange. It was statistically absurd. Even the discovery of its proportions pushed scientists to rethink how material behaves in extreme conditions. Could space weathering really carve something like that? Could interstellar collisions create such thin remnants? The physics didn't rule it out, but it did make the odds vanishingly small. As telescopes tracked Oumuamua's tumbling motion, they noticed something else. It wasn't spinning in a simple, steady rotation. Instead, it was wobbling chaotically, like a bottle tossed into the air. That suggested it had been spinning irregularly for a long time, possibly since its ejection from its original system. Each bounce off gravity fields, each brush with stellar winds, could have shifted its rotation. It wasn't just tumbling. It was dancing. The kind of dance that says, "I've seen some things." That chaotic rotation made it even harder to pin down its true form. Every time astronomers thought they had modeled the shape correctly, the light curve shifted in a way that didn't quite fit. Some nights, the glint would peak earlier or dim more slowly. It was as though Oumuamua was deliberately teasing the people trying to understand it. And here's the kicker. Its surface appeared unusually reflective. Not mirror-bright, but definitely shinier than typical asteroids, which are usually dark and dull. That reflectivity hinted that it might have a smooth or metallic surface, or perhaps be coated in organic compounds hardened by radiation. Picture a chunk of cosmic resin polished by millions of years drifting between stars. Whatever it was made of, it wasn't your average rock. The elongated or flattened shape also had practical implications. If it was that thin, it would have a high area-to-mass ratio, meaning sunlight could push it more effectively than on a denser, rounder object. That might explain its subtle acceleration as it left the solar system, without invoking gas jets or alien engines. In other words, its weird geometry wasn't just an aesthetic oddity. It might have been the key to its movement. Still, the visuals were too good to ignore. Every artist who drew it took creative liberties. Some painted it as a sleek cigar streaking past the planets. Others as a golden shard twirling like a leaf on the wind. NASA scientists joked that the only certainty was that no two depictions looked the same. In a way, that became symbolic. Oumuamua was whatever you imagined it to be. The universe had given us a Rorschach test in space. Its shape also changed the tone of how we thought about cosmic visitors. Suddenly, the universe felt less predictable. Before, space rocks were supposed to behave like space rocks. You could measure them, categorize them, file them neatly under asteroid or comet. Then along came something that looked like it was designed by an abstract sculptor with a flair for drama. The shape mystery of Oumuamua didn't just challenge our understanding of celestial mechanics. It challenged our imagination. It reminded us that the cosmos isn't limited to the patterns we expect. Out there, beyond the reach of our telescopes, there might be countless other shapes, spirals, sheets, shards, each born from strange events we can barely guess at. In the end, the argument between cigar and pancake became more than just a question of form. It became a symbol of how little we truly know. Oumuamua was a shape-shifting enigma, defying every label we tried to pin on it. Whether it was long or flat, smooth or fractured. It was undeniably something our corner of the galaxy had never seen before. It was the first interstellar object we caught a glimpse of, and it made a grand entrance, twirling through the sun's light like a cosmic mime, refusing to explain itself, and then gliding away before anyone could take a proper picture. Its brightness changed dramatically as it spun, which meant it wasn't a sphere. It was reflecting sunlight like a cosmic disco ball, flashing every 7 hours, as if the universe decided to drop the strangest mixtape ever. When Oumuamua first showed up in telescope data, it didn't just move strangely, it shined strangely. Its brightness curve, that delicate graph of how much light it reflected over time, was as erratic as a strobe light at a cosmic dance party. Every 7 to 8 hours, the brightness would rise sharply, then fade just as quickly. The pattern repeated like clockwork, a telltale sign of rotation. But the amount of change was enormous, far beyond what any round or slightly lumpy rock could produce. That meant something unusual was happening on its surface. The light curve became the key to unlocking Oumuamua's physical secrets. Since we couldn't snap a clear photo, it was far too distant and faint, astronomers had to use that changing brightness as a kind of fingerprint. The logic was simple but powerful. How bright an object appears tells you how much sunlight it's reflecting, and how that brightness varies tells you how it's turning in space. A small spherical rock would show only subtle variations. A long, thin object would flash dramatically as it presented its broadside to the sun, then dim when turned edge-on. The data painted a vivid story. Oumuamua was tumbling chaotically, not spinning neatly like a top. Every rotation sent its reflected light surging and fading by factors of 10. It wasn't just turning, it was flailing, a spinning shard glinting in the sunlight. Astronomers joked that it was like trying to analyze a lost piece of interstellar junk that couldn't stop doing cartwheels. But the reflectivity itself, the albedo, as scientists call it, was surprisingly high. Oumuamua reflected more sunlight than a typical asteroid. That immediately set it apart from the dull, charcoal-colored rocks we're used to seeing orbiting our sun. Most space debris is coated in dust, carbon-rich compounds, and the soot of eons of micrometeorite impacts. Yet this interstellar visitor gleamed, suggesting its surface was smooth, metallic, icy, or coated with something exotic. Some scientists proposed that radiation in interstellar space might have baked and hardened its outer layer, creating a kind of shiny shell. Imagine a chunk of rock drifting through the void for millions of years, bombarded by cosmic rays until it becomes a glossy relic, like stone turned to glass. That would explain why its reflections were so crisp, light bouncing cleanly off a hardened surface rather than scattering through dust. Others wondered if it might be coated in organic ices, materials rich in carbon that darken when irradiated but can also shine under certain lighting angles. It could be that the glints we saw were not from metal, but from complex molecular layers, frozen hydrocarbons formed in deep space, polished by eons of cosmic weather. The surface of Oumuamua, if we could see it up close, might look like a mix between obsidian and burnt sugar, a strange, glimmering relic shaped by time and emptiness. But there was another detail hidden in that flickering light. The pattern of its rotation suggested that Oumuamua wasn't spinning around a single stable axis. It was tumbling unpredictably, its rotation axis slowly drifting over time. In technical terms, that's called non-principal axis rotation. In plain terms, it means it was spinning like a football that had been poorly thrown, wobbling end over end. That kind of tumbling can happen when an object is hit or disturbed, maybe by a collision long ago or by a gravitational tug from a star during its journey. That motion also meant that each side of Oumuamua reflected sunlight differently. Some surfaces were likely darker, others brighter, depending on their material composition. As it spun, those differences exaggerated the light curve, creating that dazzling pulse every few hours. It was like watching a distant mirror spin under a spotlight, each flash a clue from across millions of kilometers. The 7-hour period itself was interesting. For an object only a few hundred meters long, that's relatively slow. Smaller asteroids often spin faster, completing a rotation in minutes or even seconds. The slower rotation could mean that Oumuamua was structurally fragile. If it had been spinning too fast, centrifugal force might have torn it apart. That hinted that it wasn't a solid chunk of iron or rock, but something less dense, maybe porous, maybe even hollow. The idea that it could be a lightweight fragment added yet another twist to the growing mystery. One of the oddest details came when scientists tried to match the light variations to different possible shapes. For the cigar-like model, the data fit fairly well. Long, thin, reflective on one side, dark on another. But when they tested a flattened, disc-like shape, it fit just as well. That dual possibility, cigar or pancake, wasn't just frustrating. It was a lesson in how limited our understanding becomes when all we have is light. It's like trying to reconstruct an entire sculpture based only on the shadow it casts as it spins under a lamp. The reflective pattern also told us something profound about just how alien this object truly was. Everything about its light curve screamed unfamiliar. It didn't behave like our asteroids, didn't gleam like our comets, and didn't dim like our dust-covered debris. The sun, for a few weeks, was shining on something shaped and polished by a completely different star system. The photons bouncing off its surface had traveled across the void to reach our telescopes, carrying with them a story written in flashes and fades. And perhaps the most poetic part? We only ever saw it reflect light. We never saw it shine on its own. That distinction might sound trivial, but it's symbolic. Oumuamua wasn't a beacon. It was a mirror. It reminded us that the universe doesn't always announce its mysteries with grand displays. Sometimes it just sends a piece of itself drifting by, catching a glint of sunlight, and reflecting it toward us for the briefest of moments. For those few weeks, astronomers around the world chased those flickers like moths following a flame. Every flash was a message from a traveler that would never speak, never return, and never reveal its origin. And in those silent reflections, we caught a glimpse not just of a strange object, but of the deeper truth about discovery itself. Sometimes the universe doesn't hand you a spotlight. It just lets you notice the shimmer of something passing through the dark, daring you to wonder what it means. Most icy visitors grow a visible tail as sunlight vaporizes their frozen gases. But Oumuamua didn't. It was like a comet that had gone minimalist. No flashy display, just pure mystery. Scientists started calling it a dry comet, which sounds more like a bad cocktail than a celestial category. If you've ever seen a picture of a comet, you know the drill. A glowing head and a long, graceful tail streaming behind it, like the universe's version of a sparkler. Those tails aren't just decoration, they're physics in action. When a comet approaches the sun, heat starts vaporizing its icy surface, releasing jets of gas and dust. Sunlight and solar wind push that material away, forming a bright tail that can stretch for millions of kilometers. It's how we can spot a comet from Earth long before it even gets close. So, when astronomers first suspected that Oumuamua might be a comet, they were on the lookout for that signature behavior. They pointed sensitive instruments toward it, expecting at least a whisper of vapor, some hint of outgassing, that cometary exhale of frozen gases turned to steam. But the instruments came back quiet. No tail, no coma, no detectable emission. Nothing. It was as if the object had taken one look at the sun, shrugged and said, "Not today." That silence was deafening. Every comet we've ever studied, from the dirty snowballs of the Kuiper Belt to the dramatic visitors like Hale-Bopp, reacts to sunlight in some way. Even faint comets usually display a halo of evaporated gas under high magnification. But Oumuamua remained pristine. Not a single sign of melting, vaporization, or jet activity could be found, even though it had passed closer to the sun than Mercury. At first, scientists thought maybe they'd simply missed it, that the outgassing had occurred before anyone started watching. But the math didn't add up. If it had released enough material to explain its unusual acceleration, that much gas would have left a visible mark. Telescopes trained on its path, including some of the most sensitive in the world, saw nothing but empty space around it. No glowing particles, no dust cloud, no trail, just a lone point of light slipping away. It was a problem that got under astronomers' skin. On paper, Oumuamua's motion looked like that of a comet. It sped up slightly as it left the sun, as though being pushed by a subtle force. But in reality, it behaved like a rock, silent, inert, and clean. That contradiction turned the entire discussion on its head. What do you call an object that moves like a comet but looks like an asteroid? Apparently, a dry comet. That new term didn't mean the scientists suddenly understood it. Quite the opposite. It was an admission of confusion wrapped in a label. A dry comet was a way of saying maybe it used to have ice, but the surface was now sealed beneath some kind of crust. If its outer layers had been baked by radiation during its interstellar journey, they might have turned into a carbon-rich shield, trapping the volatile gases inside. When sunlight hit it, only the faintest whiffs of gas would escape, too little to form a visible tail, but just enough to nudge it ever so slightly. It was a compelling theory, and it came with an elegant irony. Oumuamua might have been the cosmic equivalent of a comet in disguise, like a snowball that had spent too long in the oven, its frosty core still intact beneath a thick, protective shell. The sun's warmth could have caused tiny pockets of trapped gas to escape through microscopic cracks, producing that mysterious acceleration without a visible tail. If true, it suggested that interstellar space does strange things to comets. After millions of years drifting between stars, constantly bombarded by cosmic radiation, the outer layers could transform into an insulating crust, dark and carbonized. Such a surface would protect the interior from sublimating when it got close to another star. In other words, interstellar comets might all look a little dead until they decide to wake up. But not everyone bought that explanation. Some researchers argued that the lack of tail wasn't a matter of crust, it was a matter of composition. Maybe Oumuamua wasn't made of water ice at all. What if it was composed of something more volatile, like hydrogen or nitrogen ice, which could sublimate without leaving detectable traces? Hydrogen gas is invisible to most telescopes and would create little to no visible tail. If that was the case, then Oumuamua might be a fragment from the surface of an exotic exoplanet, a shard of frozen nitrogen chipped off a distant Pluto-like world and sent wandering through the galaxy. That idea made Oumuamua sound even more like an alien artifact, but of a natural kind. A relic, not of technology, but of planetary geology. A piece of some long-lost world's icy crust, journeying through the stars for untold eons before stumbling through our solar system. If so, it wasn't just a dry comet. It was a time capsule from another planetary system. Still, for many scientists, the lack of a tail was a source of both fascination and frustration. It was like trying to diagnose a patient who refuses to show symptoms. They had motion, shape, and reflection data, but no chemical signatures, no vapor lines, no glowing emissions to analyze. It was the astrophysical equivalent of trying to solve a crime when the culprit wiped the fingerprints clean. This missing tail also reshaped how astronomers thought about comet detection. Most comet hunting programs rely on spotting those bright, fuzzy tails as clues. If interstellar objects like Oumuamua routinely travel clean, then our detection systems might be missing countless others. There could be hundreds, maybe thousands of dry comets slipping silently through our solar system every decade, visible only to the instruments precise enough to catch their subtle light curves before they vanish. In the end, the missing tail became more than just an observational detail. It became a symbol of what made Oumuamua so compelling. It broke our categories. It refused to be one thing or the other. It defied the conventions we'd built to make the universe legible, And in doing so, it reminded scientists that sometimes the most important discoveries aren't the ones that shine the brightest, but the ones that don't shine at all. Oumuamua's journey through the inner solar system was a silent performance. No outbursts, no tail, no trail of dust. Just a mysterious silhouette gliding through sunlight, perfectly understated. It didn't need spectacle to leave us awestruck. Its very absence of a tail became the story. The visitor from another world came and went without a whisper, proving that sometimes the universe doesn't need to shout to get our attention. It just drifts by quietly and lets the silence speak for itself. When it started accelerating slightly as it left the solar system, everyone got nervous. It wasn't gravity doing that. Something else was giving it a tiny push, maybe outgassing, or maybe something artificial. Cue the alien memes. At first, everything about Oumuamua's exit seemed routine, at least as routine as a first-ever interstellar visitor could be. It had swooped around the sun, picked up speed from its gravitational slingshot, and was heading outward on a clean trajectory toward interstellar space. Then, as astronomers tracked its path, the data began whispering a different story. The numbers didn't line up. Oumuamua wasn't slowing down the way it should have under the sun's gravity alone. It was moving faster, just a tiny bit, but enough to matter. To most people, a tiny bit faster sounds like cosmic nitpicking. But to astrophysicists, those tiny bits are everything. Every rock, every comet, every spacecraft follows predictable physics. Gravity in, gravity out, nice and neat. When something doesn't fit that equation, it's like hearing a single wrong note in a symphony. You can't ignore it. The acceleration was subtle, almost delicate. No dramatic jet of gas propelling it forward, no visible thrust. Just a barely measurable increase in velocity, roughly 1 part in 10,000 compared to the pull of the sun. But even that minute effect was enough to bend its trajectory slightly more outward than expected. Something had pushed Oumuamua ever so gently as it sailed away. The first explanation on the table was the simplest: outgassing. In comets, as they warm near the sun, ices trapped beneath their surfaces vaporize and escape, producing tiny jets that act like thrusters. It's the same principle as air escaping a balloon. Each puff gives a little push. That could easily explain a subtle acceleration. The only problem? No one had actually seen any outgassing. Not a trace of vapor, no tail, no coma, not even the faintest wisp detectable by the most sensitive instruments. That contradiction turned the puzzle from mildly interesting to deeply weird. If it was outgassing, it was doing so invisibly, defying every expectation of how a comet should behave. And if it wasn't outgassing, what was it? Astronomers began testing other possibilities. Could radiation pressure from sunlight be responsible? After all, photons carry a tiny amount of momentum, and if Oumuamua was lightweight and reflective enough, that gentle stream of solar light could give it a measurable push. It would be like a leaf caught in a faint breeze, drifting away not because of thrust, but because light itself was nudging it along. To make that theory work, though, Oumuamua would have to be astonishingly thin, perhaps less than a millimeter thick, with a huge surface area relative to its mass. That made it sound suspiciously like a solar sail. a concept long championed by physicists as a method for interstellar travel. A structure designed to catch sunlight, accelerate across the stars, and do it all without fuel. Suddenly, the alien jokes didn't feel so much like jokes anymore. The idea that Oumuamua could be artificial, built, not born, was enough to ignite one of the most public scientific debates in recent memory. Harvard astronomer Avi Loeb famously argued that the simplest explanation might be technological. Maybe it was a piece of alien debris, or a functioning probe, or even a derelict sail drifting between stars. His argument wasn't that it must be aliens, but rather, we can't rule that out. And if not aliens, what? Most of the scientific community responded with raised eyebrows and cautious skepticism. Extraordinary claims require extraordinary evidence, and the evidence here was barely visible. No radio signals were detected, no maneuvers suggesting control, just that mysterious acceleration, whispering from the data like a riddle. Still, the debate was electric. For decades, scientists had joked that if something from outside the solar system ever appeared, it would either be totally boring or totally incomprehensible. Oumuamua turned out to be both. It didn't have the flashing lights or ominous hum of a science fiction visitor, but it didn't behave like anything natural either. It occupied the strangest possible middle ground. Too weird to be normal, too subtle to be alien. Some researchers propose that instead of sunlight, thermal recoil might be at play. Maybe the object was heating unevenly, releasing infrared radiation more strongly in one direction, like a slow-motion photon engine. That kind of asymmetric heat emission could create a small but steady thrust. The challenge, of course, was proving it. Without direct measurements, all anyone had were models, beautiful, speculative models, stacked like paper towers on a foundation of uncertainty. Others explored the possibility that Oumuamua might be composed of extremely low-density material, something almost foamy, an interstellar puffball made of dust bound loosely together. Such a fractal aggregate could be pushed by sunlight much more effectively than rock or metal. It would behave like cosmic styrofoam, light, fragile, and easily moved by the solar wind. That idea sounded almost too whimsical, but mathematically it worked. Yet, no matter how elegant the natural explanations became, the acceleration kept defying comfort. It was the nagging piece that refused to fit. Every time scientists tried to make the data conform, Oumuamua seemed to smirk and say, "Nice try." And then, like all great mysteries, it slipped away before anyone could confirm anything. Within weeks, the object had faded beyond the reach of even our best telescopes. No follow-up measurements, no second chance. Just a trail of equations, a handful of light curves, and a lot of unanswered questions. For many researchers, the experience was maddening and humbling. Science thrives on repeatability, but the universe doesn't always cooperate. Oumuamua had given us one shot, one glimpse, and left behind a puzzle that no one could fully solve. Was it an icy fragment releasing invisible gases, a wafer-thin relic of a shattered world, a piece of alien engineering adrift between stars? Each possibility sounded improbable, and yet one of them had to be true. the acceleration puzzle became more than a physics problem. It became a metaphor for curiosity itself, the push that keeps humanity searching, questioning, reaching for explanations even when the evidence slips through our fingers. Oumuamua might have been pushed by sunlight, or vapor, or physics we don't yet understand, but, in its own way, it pushed us too. It made scientists reconsider what's possible, made engineers dream of missions fast enough to chase the next one, and made the rest of us look up at the night sky a little differently. Somewhere out there, more interstellar travelers are passing silently through the dark, gliding on forces we've only begun to grasp. And maybe, just maybe, one of them will slow down long enough for us to finally catch it and ask it what all the hurry was about. A few bold researchers suggested it could be a light sail, an artificial probe pushed by starlight. Essentially, a cosmic solar panel on a road trip. The idea wasn't that it had to be aliens, just that it behaved like something aliens could make. Naturally, the internet heard only aliens. By the time the strange acceleration of Oumuamua was confirmed, the scientific community was divided between two camps, those determined to explain it through natural physics, and those who whispered, half jokingly, half seriously, that maybe, just maybe, it wasn't natural at all. It wasn't the first time humanity had looked to the skies and wondered if we were witnessing evidence of extraterrestrial intelligence. But this time the question didn't come from sci-fi enthusiasts or radio hobbyists. It came from professional astrophysicists with data in hand and furrowed brows. The alien hypothesis didn't begin as sensationalism, it began as a thought experiment. In late 2017, just months after the discovery, a Harvard astrophysicist named Avi Loeb and his postdoctoral researcher, Shmuel Bialy, published a paper proposing that Oumuamua's unusual acceleration could be explained if it were a light sail, a thin, flat structure designed to harness radiation pressure from stars. Such sails have already been tested on a small scale here on Earth, using sunlight or laser beams to propel wafer-thin spacecraft. The idea isn't science fiction, it's aerospace engineering with an interstellar twist. If Oumuamua were indeed a light sail, that would explain both its unusual motion and its lack of outgassing. No ice jets, no comet tail, just pure photon propulsion. The physics worked beautifully on paper, but the implications, they were galaxy-sized. It would mean that somewhere out there, an advanced civilization had built something capable of drifting between star systems, and by sheer coincidence, it had wandered through ours. Now, Loeb never claimed it was an alien artifact. His actual argument was far more measured. Given all possible explanations, we shouldn't rule out the artificial one. He compared it to the scientific method at its best, following the evidence wherever it leads, even if it leads to something uncomfortable. When you hear hoofbeats, he said, you think horses, not zebras. But if you're on another planet, it might actually be zebras. Oumuamua was starting to look like one cosmic zebra. The reaction, predictably, exploded. News outlets went wild. Headlines screamed about alien spacecraft in our solar system, while scientists across the world buried their faces in their hands. Memes flooded the internet. Oumuamua as a galactic Tesla, an alien USB drive, even a pizza delivery probe that got lost on the way to Alpha Centauri. Suddenly, the first interstellar object ever discovered wasn't just an astronomical event, it was a cultural one. But underneath the noise, the question remained serious. Could an alien light sail really survive a journey across the galaxy? Technically, yes. A thin, reflective sheet made of strong material, something like graphene or an advanced metal composite, could, in theory, endure millions of years adrift in space. Radiation pressure would keep it moving, and with no friction in the vacuum, it could maintain its speed indefinitely. It wouldn't even need a crew. It could be a derelict, an ancient probe whose creators had long since vanished. That concept struck a deep chord because it wasn't just plausible, it was poetic. For centuries, humans have sent messages into the void. Radio signals, spacecraft carrying golden records, digital whispers saying we were here. What if someone else had done the same, long before us? And what if one of their creations had finally, by sheer chance, brushed against our corner of the galaxy? The thought gave the entire scientific discussion a strange sense of intimacy. It wasn't about UFOs or little green men. It was about legacy, the cosmic footprints civilizations might leave behind. Of course, not everyone was convinced. Many astronomers argued that invoking aliens was unnecessary when natural explanations, however improbable, still fit the data. They pointed out that extraordinary claims require extraordinary evidence, and so far there wasn't any. No signal, no pattern of communication, no controlled motion. Just a rock, or sail, or shard, or pancake, following a path dictated by physics. To leap to aliens, they said, was to abandon Occam's razor, the principle that the simplest explanation is usually the right one. But Loeb and others countered that sometimes the simplest explanation is the extraordinary one. After all, if it looked like a light sail and behaved like a light sail, why not at least entertain the idea that it could be a light sail? That was the core of the alien hypothesis, not a claim of discovery, but a refusal to prematurely close the door on possibilities. The debate revealed an uncomfortable truth about human psychology. We're both desperate for and deeply skeptical of contact. We crave proof that we're not alone, but we also fear being the generation that cried aliens over a misidentified rock. Every side of the discussion carried its own philosophy. To some, entertaining alien explanations was bold curiosity. To others, it was reckless speculation that undermined public trust in science. In private, many astronomers admitted that the alien idea was fun to think about, just not something you wanted in your research paper if you valued tenure. Still, it energized the field in an unexpected way. Suddenly, interstellar objects weren't just cold chunks of debris. They were potential messengers. The idea sparked proposals for new telescopes, faster probes, and missions designed to intercept the next visitor. Oumuamua, alien or not, had made everyone realize we weren't ready for this kind of encounter, natural or otherwise. Even years later, as more data poured in and alternative explanations gained traction, the alien probe theory refused to die. It had entered the cultural bloodstream, not because it was proven, but because it captured something essential about human nature: the need to wonder. The moment we saw something from beyond our solar system, we didn't just analyze it, we anthropomorphized it. We imagined purpose, intention, design. It's what humans do best. We tell stories about the unknown until they make emotional sense. In the end, whether Oumuamua was a piece of alien technology or just a cosmic oddball doesn't really matter. The alien hypothesis served a deeper purpose. It reminded us to stay curious, to question our assumptions, and to recognize that the line between imagination and discovery is often paper thin. Because maybe, just maybe, one day we'll detect another interstellar traveler, and maybe this time, when we point our instruments toward it, we'll find a shape too perfect, a rotation too regular, a pattern too deliberate to ignore. And then, somewhere across the stars, someone might be watching their own sky and saying, "Wait, what was that?" Most scientists tried to keep both feet on the ground, metaphorically, because literally they were staring at the sky, and proposed more natural ideas. Maybe Oumuamua was a fragment of a shattered planet, or a chunk of nitrogen ice from a faraway world. Space debris, but make it interstellar. After the alien sail buzz began to fade, the scientific community returned to its comfort zone, explaining the weird with the laws of nature. The majority of astronomers, planetary scientists, and physicists weren't ready to rewrite the definition of natural object just yet. Sure, Oumuamua's shape, motion, and behavior were bizarre, but the universe specializes in bizarre. It was far more likely, they reasoned, that this object wasn't built. It was born, somewhere in a distant system where the rules of geology, chemistry, and gravity had simply played a different tune. One of the earliest theories was that Oumuamua might be a fragment from a planetary collision, essentially cosmic shrapnel. In young star systems, planets and asteroids crash into each other all the time. Those collisions can hurl debris outward at incredible speeds, some of it fast enough to escape the gravity of its parent star entirely. Once ejected, that debris becomes an interstellar vagabond, drifting through the galaxy for millions or billions of years. Oumuamua could have been one such fragment, a jagged splinter torn from the crust of a destroyed world, carrying with it the scars of its violent birth. This idea neatly fit one of the object's most distinctive traits, its elongated or flattened shape. A catastrophic impact could produce debris stretched by tidal forces or pressure waves. And over countless eons, that fragment might have been smoothed and weathered by cosmic radiation until it resembled the tumbling shard we saw. Space isn't kind to wanderers. Micrometeorites, ultraviolet light, and charged particles constantly chip away at their surfaces. After enough time, what started as a rough piece of rock could become sleek and reflective. An interstellar skipping stone polished by eternity. But even the collision theory had its issues. Most rocky fragments tend to be denser and darker than Oumuamua appeared to be. Its reflectivity hinted at a lighter, possibly icy composition. So another school of thought emerged. Maybe it wasn't rock at all. Maybe it was ice, just not the kind we're used to seeing. The nitrogen ice hypothesis quickly became one of the leading contenders. Scientists like Alan Jackson and Stephen Desch proposed that Oumuamua could have originated from the surface of a Pluto-like planet. In other words, it might be a chunk of frozen nitrogen that had been knocked loose from the crust of a distant, icy world in another solar system. Pluto, for instance, has a surface rich in solid nitrogen that sublimates when warmed by sunlight. If another planetary system had its own version of Pluto, a massive impact there could have ejected frozen fragments into space, and one of those could have wandered into ours. This nitrogen theory was appealing for several reasons. For one, it explained the missing tail. Nitrogen ice sublimates cleanly and quickly, leaving little visible debris. The escaping gas would be invisible in most wavelength, and yet the process could still generate the subtle acceleration Oumuamua displayed. It also explained the object's brightness. Nitrogen ice reflects sunlight well, much better than dusty rock or carbon compounds. And its flat shape could make sense too. As it sublimated during its long journey through space, its softer layers might have evaporated unevenly, leaving behind a thin, flattened remnant, like a cosmic bar of soap worn down by time. Another camp suggested hydrogen ice instead of nitrogen. This was an even stranger proposal. A block of nearly pure hydrogen, frozen solid in the cold depths of a molecular cloud, the nurseries where stars are born. Hydrogen is notoriously difficult to keep solid, even at extremely low temperatures, but if such a fragment somehow formed and survived, it could explain Oumuamua's motion perfectly. Hydrogen sublimation would produce thrust without leaving any visible trace. The problem, of course, was plausibility. Could a chunk of hydrogen ice really survive the violent birth of a star and then journey across interstellar space for millions of years without evaporating? It was a stretch, but so was everything about Oumuamua. Then came the dust aggregate theory, a less glamorous but surprisingly convincing idea. Maybe Oumuamua wasn't solid at all, but rather a fluffy clump of dust held together by weak electrostatic forces like a cosmic snowflake. This kind of low-density object would be easily pushed by sunlight, explaining the gentle acceleration without requiring any outgassing or exotic material. It would also account for the faint brightness. Porous objects scatter light in complex ways, producing the kind of unpredictable reflections we observed. If true, Oumuamua wasn't a shard or an artifact, but the interstellar equivalent of cosmic lint, delicate, ancient, and absurdly persistent. Of course, every natural theory came with its own headache. If it was rock, why was it so bright? If it was ice, why didn't we see gas? If it was dust, how did it hold together over such a long journey? Each explanation solved one part of the puzzle while breaking another. The mystery of Oumuamua wasn't that we lacked hypotheses. It was that we had too many, and none of them fit perfectly. But that's the beauty of science. Each new theory, no matter how odd, pushes the conversation forward. The nitrogen ice camp started modeling collisions on exoplanetary Plutos. The dust aggregate supporters began running simulations of interstellar survival times. Even the skeptics, those who insisted Oumuamua was nothing but a weird rock, had to refine their models of how solar heating might subtly alter trajectories. The debate became less about what Oumuamua was and more about what it could teach us about other solar systems. In the end, the consensus leaned toward a natural explanation, but with an asterisk, a cosmic shrug that said, probably natural, but undeniably strange. After all, space has a way of making ordinary physics look extraordinary. A fragment from another world weathered and reshaped by forces beyond imagination, could easily appear alien to us simply because we've never seen anything like it before. So maybe Oumuamua wasn't a message, or a machine. Maybe it was just an accidental ambassador, a chunk of frozen memory from a shattered planet light years away, drifting silently through our sun's glow. And if that's true, then it's still miraculous. Because for the first time, we weren't just looking at something from another world. We were holding, for a brief moment, the story of another star's history written in stone and ice. The weird acceleration might be explained if the object was made of something very light and reflective, like hydrogen or nitrogen ice that sublimates easily. That would give it a subtle push without needing alien thrusters. In other words, it could be a frozen snowflake the size of a football field. When scientists began running the numbers on Oumuamua's motion, they quickly realized the explanation had to lie in what it was made of. Its mysterious little boost wasn't magic, it was chemistry and physics in disguise. Somewhere in its strange composition lay the key to how it had traveled so far, survived so long, and yet remained so ghostly and elusive. The problem was that no known material, at least none seen in our solar system, fit all the clues at once. It was as if nature had handed astronomers a jigsaw puzzle, but a few of the pieces came from another box entirely. To start, any material capable of producing that slight acceleration without leaving visible traces had to be both lightweight and volatile. In space terms, volatile doesn't mean unpredictable. It means easily vaporized when heated by sunlight. Cometary ices fit that description. Water, carbon monoxide, carbon dioxide, methane, ammonia. They all sublimate, turn directly from solid to gas when they get warm enough. But Oumuamua showed no visible outgassing at all, so whatever was driving it had to be stealthier than the usual comet cocktail. That's where hydrogen and nitrogen came in as the leading suspects. Both are incredibly light, reflective when frozen, and prone to rapid sublimation. If Oumuamua were made primarily of either, sunlight could easily vaporize small amounts, providing just enough thrust to explain its acceleration, like a whisper of air pushing a feather. At the same time, the escaping gases would be invisible in most wavelengths, hiding their tracks from even our best telescopes. It was a clean, elegant solution. But the elegance came with a catch. Frozen hydrogen and nitrogen are among the most fragile substances in the cosmos. They exist only at temperatures near absolute zero and are easily eroded by cosmic radiation. The galaxy is not exactly gentle. It's filled with high-energy particles and stray photons that shred molecules over time. For an object made of such delicate material to survive a million-year journey through interstellar space seemed, frankly, absurd. So scientists started doing the math, because nothing kills absurdity faster than numbers. If Oumuamua was roughly 100 meters long and made of hydrogen ice, how long could it last before vaporizing completely? Calculations showed it would have to be traveling for far less than 1 billion years, maybe only a few tens of millions, before arriving here. That meant it might have been ejected from a nearby star system, one that formed relatively recently on the galactic timescale. Suddenly, the object's journey didn't seem quite as impossible. For nitrogen ice, the numbers worked out even better. Nitrogen is less volatile than hydrogen, but still sublimates easily enough to generate thrust. It also forms large, smooth surfaces when frozen, just like the plains seen on Pluto, which are made almost entirely of solid nitrogen. That realization turned heads. What if Oumuamua wasn't just random debris, but a piece of a nitrogen-rich exoplanet's crust? Imagine a Pluto-like world orbiting another star, struck by a massive collision that blasted chunks of its frozen surface into space. Some of those fragments could escape their system entirely, drifting into the galactic void, and one of them, after millions of years, might have wandered straight into our solar system. That scenario elegantly explained nearly everything: the reflectivity, the acceleration, the absence of a tail, even the flat shape. Nitrogen ice sublimates unevenly, eroding surfaces in a way that can flatten irregular objects over time, like a slowly melting snowball squashed by heat and radiation. If that was the case, then Oumuamua might literally have been a cosmic snowflake, formed in the cold of another world and preserved just long enough for us to catch a glimpse of it before it evaporated into history. However, the nitrogen model still left one nagging issue: probability. How many exoplanets like Pluto would need to exist, and how many collisions would have to occur for one of their icy shards to randomly pass through our solar system just as we were advanced enough to notice it? The odds seemed minuscule. Yet, space doesn't play by casino rules. Given the sheer number of stars and planetary systems out there, even the most unlikely events can happen all the time. It's just that we don't usually get front-row seats. There were also stranger suggestions, materials so exotic they bordered on science fiction. Some researchers wondered if Oumuamua could be composed of solid molecular hydrogen wrapped in a crust of organic compounds, or even a rare kind of carbon structure formed under extreme pressure, like graphite or graphene. These materials could theoretically reflect sunlight efficiently and weigh very little. A hydrogen-graphene hybrid drifting through interstellar space sounds like a futuristic spacecraft material, but it could also be the natural outcome of chemistry, playing with different conditions than we have on Earth. Others leaned into the fluffy aggregate idea, suggesting that the material wasn't solid at all, but a loosely bound matrix of dust and ice, so porous that it behaved more like aerogel than rock. If Oumuamua were that light, even faint radiation pressure could move it. In essence, the material mystery might not have been what it was made of, but how it was structured. Not a chunk, but a cloud held together by electrostatic cohesion. Every model, hydrogen, nitrogen, dust, or something in between, forced scientists to confront how little we know about the diversity of matter beyond our solar system. We've studied plenty of rocks, ices, and gases here, but what happens when those same ingredients are cooked under alien conditions? A planet born around a different type of star might produce materials we've never even imagined. Oumuamua could be a natural sample of cosmic chemistry we've never encountered before. In the end, the material mystery became less about identifying one substance and more about expanding our sense of possibility. The universe might be full of impossible materials, objects that don't fit neatly into our categories of rock or ice or dust. Oumuamua could have been our first clue. As it faded into the dark, one thing became clear. Whatever it was made of, it worked. It survived unthinkable distances, endured the heat of the sun, and performed an interstellar disappearing act with perfect timing. Maybe the true mystery wasn't the material itself, but the message it left behind. That nature, when given enough time and space, can create things that look like magic and still play by the rules of physics. Oumuamua didn't just rotate, it tumbled chaotically, like a phone dropped in zero gravity. That made it nearly impossible to pin down its true shape. Every measurement was like trying to photograph a banana that won't stop pirouetting. When astronomers first noticed that Oumuamua's brightness was changing dramatically every few hours, they assumed it was rotating in a predictable way, like most asteroids and comets do. But as the data piled in, it became obvious this object wasn't spinning politely around a single axis. It was doing something far more theatrical. It was tumbling, wobbling, and twisting through space in a motion so irregular that it looked almost animated. If a normal asteroids are cosmic ballerinas, Oumuamua was interpretive dance, graceful, yes, but utterly unpredictable. Rotation in space is usually simple. An object spins around its principal axis, and unless something disturbs it, it'll keep doing so indefinitely. It's Newton's first law in action: steady, stable, and mathematically elegant. But when a body's mass isn't evenly distributed, or when it's been struck or torqued, its motion becomes chaotic. The spin doesn't line up with its shape anymore, and it begins to tumble, like a tossed baton flipping end over end. This kind of non-principal axis rotation, as physicists call it, is rare among large bodies because it tends to smooth out over time. Yet here was Oumuamua, an interstellar traveler, flaunting the most erratic spin astronomers had ever seen. That tumbling was more than a curiosity. It was a problem. Every time the object flipped or twisted, the sunlight reflected off it in wildly different ways, causing huge fluctuations in brightness. The result was a light curve so jagged and irregular that no single model could fit it perfectly. Some astronomers compared the process to trying to determine the shape of a tossed coin using only the glint of sunlight bouncing off it as it spins. Others said it was like trying to measure a fish while it's still wriggling in midair. This chaotic rotation hinted at a violent past. Stable spins don't just fall apart on their own. Something had to have disturbed Oumuamua long before it entered our solar system. Perhaps it was born tumbling, flung out of its home system by a collision, or close encounter with a massive planet. Imagine a fragment torn loose from a larger body, spinning wildly as it escaped into the void. Over millions of years, the frictionless emptiness of interstellar space would have preserved that motion indefinitely. No air, no drag, no friction, just endless spinning. The idea that it had been tumbling for millions of years gave the object a strange kind of melancholy. Here was a cosmic castaway, spinning endlessly through darkness, untouched since its violent ejection. It was like a message in a bottle that had been adrift so long that even the bottle itself forgot where it came from. The irregular spin also complicated efforts to understand its structure. Astronomers typically use brightness variations to estimate an object's shape. But if it's rotating chaotically, the math becomes an uphill battle. One moment, it appears long and narrow. The next, flat and wide. Depending on the orientation, the same data could suggest a cigar, a pancake, or a potato. Every telescope captured a different phase of its tumble, and every analysis returned a different sketch. Oumuamua was, in effect, performing a cosmic magic trick, changing its silhouette faster than scientists could take notes. But the tumbling wasn't entirely random. Careful modeling revealed that its rotation followed a pattern, albeit a complex one, governed by physics. It was precessing, its spin axis wobbling like a slowing top. The rate of that wobble suggested that its interior wasn't uniform. There might have been slight variations in density or structure that made its rotation uneven. Maybe it had internal cavities, pockets of empty space, or fractures that shifted its balance. Whatever its internal makeup, it wasn't a simple chunk of rock. It was a layered, dynamic object that carried the fingerprints of its formation and history in its spin. Interestingly, the rate of its tumbling also told us something about its strength. If it had been fragile or loosely held together, the centrifugal forces from such an irregular spin would have torn it apart. The fact that it stayed intact suggested it was either a solid monolith or held together by strong internal cohesion. That finding ruled out some of the fluffier theories. Oumuamua wasn't a delicate puff of dust. It was tough, whatever it was. The chaotic motion also affected how sunlight heated it. Different sides were exposed at different angles, causing uneven warming across its surface. That, in turn, could have influenced any sublimation or outgassing it experienced, which might even have contributed to its acceleration. In other words, the tumble wasn't just a byproduct of its past. It might have played an active role in how it behaved as it left the solar system. The way it spun could have subtly shaped its destiny. Some researchers found poetry in that. Oumuamua wasn't gliding through space with purpose. It was stumbling through eternity, yet somehow still moving forward. It was the celestial equivalent of improvisation, unpredictable but mesmerizing, disorder giving rise to beauty. Every glint of light we caught from it was a moment in its dance, a flicker of sunlight on an object that had been performing unnoticed in the dark for eons. If there was one thing the tumbling made clear, it was that Oumuamua had a story. Its motion was evidence of trauma, survival, and time. Maybe it was a relic from a shattered planet, a splinter of something once whole. Maybe it had collided with another fragment in deep space and been sent spinning into the galactic current. Whatever the cause, its erratic dance was the record of that history, a fossilized movement preserved across light years. By the time it passed beyond our telescope's reach, its spin remained one of the last unsolved pieces of the puzzle. Scientists could only extrapolate, guessing how it would continue tumbling as it disappeared into the dark. Even now, somewhere beyond the edge of our solar system, Oumuamua is still twisting, rolling, and flashing as it drifts farther away, its irregular rhythm continuing unseen. We may never know what final shape it truly had or what forces set it tumbling. But maybe that's fitting. In a universe where everything eventually finds equilibrium, Oumuamua was a rare exception, a perpetual motion of mystery. Its endless spin was the universe's way of saying that not everything has to settle down. Not everything has to make sense. Some things just keep dancing through the dark, spinning stories we'll never fully read. After a few short weeks of observation, it was gone, vanished into deep space forever. We never got another look. It was like meeting the most interesting stranger at a party, and they leave before you even get their name. For astronomers, Oumuamua's brief visit felt like the ultimate cosmic tease. One moment, it was there, flashing across telescope lenses, rewriting textbooks, inspiring midnight debates. And the next, it was gone, fading faster than the data could be analyzed. From discovery to disappearance, humanity's first encounter with an interstellar object lasted less than 2 months. 8 short weeks to study something that had spent perhaps 1 billion years wandering through the galaxy. The universe, it seems, does not believe in slow introductions. As the object receded beyond the range of our most powerful instruments, there was a collective sense of unfinished business. Every measurement, every theory, every simulation ended with the same frustrating caveat: we'll never know for sure. Astronomers are used to mysteries, but they prefer ones that can eventually be solved. Oumuamua didn't play by that rule. It left behind an incomplete puzzle, an empty space in the data that no future observation could fill. That sense of loss was palpable in the scientific community. Not the dramatic, cinematic kind, but the quieter heartbreak of missed opportunity. Researchers had glimpsed a once-in-history event, something entirely new, and they hadn't had enough time or the right tools to fully study it. It was like trying to identify a bird species from a single feather blown past your window. But even as it disappeared, Oumuamua left behind something just as valuable as itself: a legacy of curiosity. It changed how we look at the night sky, and more importantly, how we prepare for surprises hidden within it. Before its arrival, astronomers assumed that interstellar visitors, if they existed at all, would be rare beyond belief. Now, that assumption was gone. The discovery proved that the galaxy isn't a quiet, isolated place. Star systems trade debris the way cities exchange pollution. Bits of matter constantly drifting, colliding, and crossing invisible borders. In a way, Oumuamua expanded the boundaries of our imagination. It showed that our solar system isn't a closed chapter in the cosmic story, but a page in an ever-growing anthology. Every interstellar object that passes through carries a piece of another world's history, a sample of foreign geology, chemistry, and maybe even the echoes of alien weather patterns. Suddenly, astronomy wasn't just about looking outward, it was about recognizing that out there sometimes comes here. Its fleeting visit also transformed the way scientists approached the hunt for future interstellar guests. Before Oumuamua, surveys like Pan-STARRS were primarily focused on near-Earth asteroids, potential threats, not cosmic tourists. Afterward, the field evolved. Telescopes were retasked to scan deeper and faster, not just to protect our planet, but to intercept knowledge itself. The message was clear. Next time something like this shows up, we have to be ready. That call to readiness took concrete form in new projects. NASA and the European Space Agency began investing in more sensitive survey systems capable of detecting faint, fast-moving objects from greater distances. The Vera Rubin Observatory, set to revolutionize sky mapping, was designed partly with Oumuamua's legacy in mind, to catch the next interstellar visitor before it's already halfway out the door. And beyond observation, people began thinking about interception. Could we one day launch a probe fast enough to chase an object like this before it disappears into the dark again? That idea, once laughably ambitious, has grown into serious engineering studies. Concepts like Project Lyra propose using gravity assists and advanced propulsion systems to send a spacecraft after Oumuamua, or after the next one, to capture close-up images, take samples, and solve the mysteries that telescopes can't. It's a challenge that sits at the intersection of curiosity and obsession. Humanity's refusal to let go of a question once it's been asked. Culturally, Oumuamua became something more than a scientific anomaly. It seeped into books, art, films, and music. Writers called it the messenger, the wanderer, the silent visitor. It became a symbol of cosmic humility, a reminder that the universe doesn't revolve around us, but occasionally lets us peek into its deeper machinery. In coffee shops and lecture halls alike, people found themselves talking about it, marveling at how something so small could carry such enormous meaning. The story also had a philosophical aftertaste. Oumuamua reminded us of the fragility of opportunity. Even with our advanced telescopes and decades of preparation, we were caught off guard. It arrived unannounced, stayed briefly, and left us with questions instead of answers. It was a cosmic version of life's oldest lesson. Sometimes, you don't realize how rare a moment is until it's already gone. Still, it wasn't all frustration. The fact that we did notice it at all was a triumph, a sign of how far human observation has come. A century ago, we would never have detected it. 50 years ago, we might have seen the light curve but missed its interstellar origin. It took a network of advanced instruments, lightning-fast communication between observatories, and a world full of curious minds to even catch that glimpse. In that sense, Oumuamua wasn't just a visitor. It was a milestone, marking the moment humanity became capable of noticing visitors at all. Its departure also sparked a new kind of optimism. If we've seen one interstellar object, that means there must be others. Thousands, maybe millions, passing through the galaxy at any given moment. Statistically, one of them will eventually come close enough, slow enough, and bright enough for us to study in detail. We missed the first one, yes, but we'll be ready for the encore. Even now, years later, when astronomers discuss Oumuamua, there's a wistful tone in their voices. They talk about it the way you talk about a stranger who left a lasting impression, a fleeting encounter that makes you wonder what else is out there, waiting to pass your way. Some mysteries are meant to stay unsolved, at least for a while. And maybe that's the real legacy of Oumuamua. It reminded us that science isn't just about answers, it's about wonder. The universe doesn't owe us explanations. It owes us curiosity. And for a few brief weeks in 2017, a strange, silent traveler from another star gave us exactly that. Then it slipped away, leaving humanity standing under the night sky, blinking at the emptiness, and smiling at the thought that somewhere out there, in the deep dark, it's still spinning. An interstellar enigma carrying our collective awe into eternity. Its brief visit sparked a whole new field of research into interstellar objects. We realized our solar system might be full of such wanderers. Cosmic tourists just passing through, The discovery was a reminder that we are not alone in galactic traffic. When Oumuamua zipped through and vanished into the black, it didn't just leave scientists scratching their heads, it left behind an entirely new scientific frontier. Before its discovery, astronomers had theorized that bits of other star systems must occasionally drift through ours, but the idea was treated more like trivia than expectation. The chances of actually spotting one were considered practically zero. The sky is vast, and most objects are too faint, too fast, or too fleeting to catch. Then, suddenly, one showed up. That single detection flipped a footnote of theory into a brand new field of study overnight. The aftermath began with a collective realization. If we happened to catch one interstellar object during just a few years of observation, that meant there must be many more out there. You don't win the cosmic lottery on your first try unless the odds were never that bad to begin with. Statistically speaking, Oumuamua's detection implied that our solar system might be regularly visited by wanderers from other stars, millions of them silently crossing the sun's gravitational zone over time. The universe, it seemed, was far busier than we'd imagined. That revelation forced scientists to rethink how planetary systems work. Every young solar system, ours included, forms out of a spinning disk of gas, dust, and rock. Planets take shape. Some get too close to giants like Jupiter or Saturn, and gravity flings them outward like cosmic slingshots. The same thing happens elsewhere, meaning each star becomes a fountain of debris, constantly ejecting fragments into interstellar space. Over billions of years, the galaxy fills up with leftovers, asteroids, comets, and planetary crumbs. These are the nomads of the Milky Way, drifting endlessly between stars. Oumuamua wasn't a fluke. It was evidence of an entire galactic ecosystem. Almost immediately, astronomers began to hunt for more. Telescope networks combed through old data archives, searching for faint, fast-moving streaks that might have been missed. New detection algorithms were written, specifically tuned to look for objects on hyperbolic orbits, those unmistakable signs of visitors from beyond. Researchers started using terms like interstellar population density and galactic interchange. For the first time, we weren't just studying our solar system. We were studying how solar systems interact with each other. And then, not even 2 years later, the universe rewarded that vigilance. In 2019, astronomers spotted another interstellar traveler, 2I Borisov. Unlike Oumuamua, Borisov was unmistakably a comet. Tail, coma, and all. It was the cosmic equivalent of a loud tourist shouting, "I'm not from around here," where everyone could see. Its discovery confirmed what many had started to suspect. Interstellar visitors weren't rare miracles. They were part of the natural rhythm of the galaxy. Borisov's arrival helped anchor what Oumuamua had hinted at. Suddenly, scientists could compare two visitors, one silent, solid, and baffling, the other bright, gassy, and familiar. That comparison launched a new era in planetary science. Researchers began to wonder, how different are the materials between star systems? Do other solar systems make comets richer in certain ices, or asteroids composed of elements we barely see here? If we could collect enough data on interstellar objects, we could start mapping the galaxy's chemistry, one stray fragment at a time. This new field quickly got its own nickname, interstellar archaeology. The idea was that each object from another system carries a record of its birthplace, its mineral makeup, isotope ratios, and surface weathering tell the story of the star it once orbited. If we could catch and study enough of them, we could piece together a map of how different planetary systems form, evolve, and die. It was like collecting cosmic fossils, except the dinosaurs were made of ice and rock and traveled at tens of kilometers per second. The excitement extended beyond pure astronomy. Engineers, mission planners, and even space agencies began drafting blueprints for how to intercept future interstellar objects before they vanish. Concepts like Project Lyra proposed high-speed spacecraft designed to launch within months of a detection, using powerful gravity assists and advanced propulsion to chase these visitors down. The idea was audacious but not impossible. If we could predict their trajectories early enough, we might one day catch one, photograph it up close, maybe even sample it. Oumuamua had shown us the door. The next goal was to walk through it. Meanwhile, theorists began to explore the larger implications. If fragments from other star systems are constantly passing through ours, then the reverse must also be true. Bits of our own solar system are out there, drifting among the stars. Tiny asteroids ejected by Jupiter's gravity billions of years ago could be crossing alien skies right now. In that sense, we're not just receivers of galactic visitors, we're contributors. Our solar system participates in a kind of cosmic exchange program. Planets collide, fragments scatter, and star systems unknowingly trade material like postcards flung across the Milky Way. That idea carries a deeper, almost philosophical resonance. If interstellar debris can travel between systems, then the seeds of planets, maybe even of life's building blocks, could be spreading throughout the galaxy. It lends weight to the concept of panspermia, the possibility that the ingredients for life don't stay confined to one world, but hitch rides across the stars on rocks, dust, and ice. Oumuamua may not have been carrying life, but it symbolized a universe far more interconnected than we once thought. In the years since its passing, entire conferences have been dedicated to interstellar object science, a field that didn't even exist before 2017. New detection networks like the Vera C. Rubin Observatory and the upcoming Near-Earth Object Surveyor are expected to find many more such travelers. Some estimates suggest we could spot one every year once the next generation of telescopes comes online. What was once a singular, fleeting event is now the start of a new era in exploration. And, perhaps most importantly, Oumuamua's legacy changed how we think about our place in the cosmos. We're not an isolated solar system floating quietly in space. We're a stop along a galactic highway, one tiny intersection in a sprawling web of motion and exchange. Every now and then, something drifts through our neighborhood, a visitor from another sun, carrying with it a whisper of somewhere else. In its wake, Oumuamua left us with more than unanswered questions. It left us perspective. It taught us that the Milky Way is alive with movement, filled with travelers, wanderers, and relics that remind us how shared our universe really is. We might not have neighbors we can talk to yet, but we definitely share the same roads. And every once in a while, one of them passes close enough for us to notice, waving as it goes. 2 years later, another interstellar visitor named Borisov arrived, this time clearly a comet. That proved these encounters weren't one-time flukes. Oumuamua was just the mysterious first, like the pilot episode of the universe's most confusing series, and we're all still waiting for the next season. When Oumuamua vanished into the dark, it left behind a universe full of questions and one enormous expectation. Would we ever see another? For months, astronomers scanned the heavens, half hopeful and half skeptical that lightning could strike twice. Then, in August of 2010, a humble amateur astronomer in Crimea named Gennady Borisov spotted a new object moving against the backdrop of stars. At first it looked like just another comet, but then the orbital data came in, and jaws dropped all over again. This one wasn't from around here either. Humanity had just detected its second interstellar visitor, officially named 2I Borisov, 2I for second interstellar. It couldn't have been more different from its enigmatic predecessor. Where Oumuamua was elusive, Borisov was loud, flashy, and unmistakably cometary. It sported the classic glowing coma and long tail of dust and gas, broadcasting its icy nature for all to see. There was no question about its composition or origin. This was a bona fide comet from another star system, entering ours like a blazing announcement that interstellar wanderers weren't the stuff of cosmic coincidence. They were part of the galactic routine. Borisov's arrival immediately changed the tone of the conversation. Where Oumuamua had left scientists divided and speculative, Borisov brought consensus and data. At last, astronomers could study an interstellar object with confidence. Telescopes across the world, and even in orbit, turned toward it, capturing everything from its spectrum to its dust composition. The results painted a portrait of something both familiar and foreign. At first glance, Borisov looked like an ordinary comet: icy core, dusty tail, evaporating gases. But its makeup carried subtle clues that hinted at a different kind of chemistry. Spectral analysis showed high concentrations of carbon monoxide, far greater than typical solar system comets. That meant it formed in a much colder environment, perhaps on the outer fringes of its home system, where even carbon monoxide could freeze solid. Our comets, forged closer to our sun, never had that luxury. Borisov was a messenger from a frostier realm. As it moved through our solar system, astronomers tracked its trajectory with obsessive precision. Unlike Oumuamua, which darted through at breakneck speed and an awkward angle, Borisov followed a slower, more graceful path, still interstellar, but easier to observe. It passed closest to the Sun in December 2019 and remained visible for months. For once, humanity had time to take a good, long look. Every observation reinforced one idea. Borisov was proof that our galaxy is filled with planetary systems much like our own. It wasn't some alien artifact or exotic anomaly. It was just another comet, born around another star, ejected by gravitational chaos and set adrift. If Oumuamua was the cosmic mystery, Borisov was the cosmic confirmation. The universe, it seemed, had a way of balancing its riddles with its answers. Still, Borisov wasn't without its own surprises. When astronomers used the Hubble Space Telescope to peer at it up close, they discovered that it was disintegrating faster than expected. Its nucleus, roughly 1 kilometer across, was crumbling, shedding pieces as it approached the sun. By mid-2020, it had largely broken apart. It was as if the stresses of a new solar environment proved too much for a traveler used to colder, quieter conditions. Even in death, though, Borisov was generous. It released a wealth of material that telescopes could study in detail, revealing its internal composition in a way no distant observation ever could. The chemistry of that debris confirmed what many suspected. Borisov's home system was built from the same cosmic ingredients as ours: hydrogen, oxygen, carbon, nitrogen, the fundamental building blocks of everything familiar. Different proportions, perhaps different histories, but the same essential elements. It was comforting in a strange way. Across the galaxy, in star systems light years apart, nature was playing with the same set of tools. The universe might be diverse, but it was built on shared blueprints. Borisov also gave planetary scientists something precious: context. With 2 interstellar objects on record, they could begin to build models of how often such travelers might pass through. Statistical estimates suggested that at any given moment, thousands of interstellar comets might be wandering through our solar system's outer regions, invisible to us simply because they're too small or too dim to detect. Our telescopes had only just become sensitive enough to spot them. What once seemed miraculous now felt inevitable. And so, a new era of astronomy took shape. Oumuamua had raised questions. Borisov provided a foundation. Together, they redefined what local space meant. Our solar system was no longer an isolated island. It was a port on a galactic trade route, occasionally visited by ships from distant shores. The discovery also fueled imagination in ways even scientists didn't expect. If comets like Borisov could survive the journey between stars, could they carry organic molecules, those complex carbon-based precursors to life, across light years? It wasn't just poetic speculation. Data from Borisov's spectral readings suggested the presence of organic compounds in its dust. That opened the door to a profound possibility. Maybe comets like these act as couriers of chemistry, spreading life's ingredients from one system to another. Perhaps interstellar comets are the universe's version of pollen, drifting through space to seed new worlds. By the time Borisov faded from view in 2020, humanity's relationship with interstellar visitors had changed completely. We were no longer waiting for the next anomaly with disbelief. We were expecting it. Scientists began designing early warning systems capable of spotting similar objects before they got too close. Missions were proposed to intercept future ones, to collect samples, and to study them up close. The next visitor wouldn't just be observed, it would be met. Borisov may not have carried the mystery of Oumuamua, but it carried something even more valuable: proof that the universe plays by patterns. It told us that our cosmic neighborhood is alive with motion, that debris and dust are constantly exchanged across star systems, and that we're participants in an invisible galactic network older and grander than anything humanity ever built. And as Borisov drifted away, its disintegrating remnants dissolving into the dark, It left us with one final gift: anticipation. If the first visitor was the question, and the second was the answer, then the next one might be something entirely new, a story that ties the two together. The galaxy's greatest series has begun, and we've only seen the opening episodes. Somewhere out there, another interstellar traveler is already on its way, and this time we'll be ready to greet it before it slips back into the stars.